And here we're back, starting with chapter 8, the last chapter um, of this lecture on approximation algorithms. And in this chapter, we're going to consider the metric version of the traveling salesperson problem. So we just talked about traveling salesperson in the previous chapter, and now we consider a variant, a restriction, which satisfies the triangle inequality of metrics for mathematics. And we're going to learn about Christofides algorithm, which is an approximation algorithm with guaranteed approximation ratio. So this is the difference between a heuristic and an algorithm. For an approximation algorithm, we we're supposed to prove an approximation ratio to prove that an algorithm will never return a solution that is worse by more than a factor of 2 compared to the original, to the best optimal solution. So this is kind of like online algorithms, which we've analyzed using competitive ratio, right? So in online algorithm, we analyzed how much worse our online algorithm can be at most in comparison, in relation to the omniscient optimal offline algorithm. And here we compare our polynomial time algorithm to an optimal algorithm, but this optimal algorithm may in general have exponential running time. So that's a case for Christofides algorithm, which is not a heuristic. And we similarly look at the knapsack problem, which we've just considered. And first we're going to devise an algorithm for this problem, which is an exponential time algorithm. We don't like exponential time algorithm, but it's a special kind of exponential time algorithm, namely it's called strongly polynomial time. This is a misleading name. We will clarify that when we're there. But the benefit of this algorithm, which is based on dynamic programming, is that this algorithm can be used, can be adapted again, kind of like with meta programming, to turn that exact algorithm into a faster approximation algorithm. So this is a general method. For some problems, one can convert exact exponential time algorithms into polynomial approximation algorithms. And such problems are called fully polynomial time approximation schemes for reasons that I will then explain. And then we'll discuss the limits of approximability. We will see that some problems cannot be approximated unless, of course, P is equal to NP, unless there exists polynomial time algorithms for the original problem, for the exact problem. Okay, so let's dive in and consider the metric traveling salesperson problem. So remember, what is the traveling salesperson problem? There we're given a graph, an undirected graph with edge weights. And the question or the goal is to find a cycle, like with Hamiltonian circle, but a cycle of shortest length as an optimization, as a minimization problem. Okay, and here's a formalization. So traveling salesperson problem as a decision problem. Reformulation of the original minimization problem is given a graph and giving edge weights W. So that is, every pair of vertices is assigned some natural number. That's the cost of traversing the edge between these two vertices. And if in our graph our edge is absent, then we just can, we don't need to consider that separately. That can be incorporated by saying that traversing this edge, absent edge, is just very expensive, meaning that the edge weight between these two vertices is very, very large. And so by choosing the edge weight sufficiently large, it is no loss of generality. We can always suppose that the underlying graph is a complete graph, right? So that's a Turing salesperson problem. And as a decision problem, the question is whether it has a Turing sales tour of weighted length, sum of the edge weights at most k, where k is this input parameter. This is our standard way of converting optimization problems into decision problems. So when we now consider the Christofides algorithm, the input are again these edge weights, natural numbers, non-negative. It's important to have non-negative edge weights, otherwise it might be beneficial to run in cycles, and a negative cycle will decrease the cost of the weight. So this is the first condition for the metric traveling salesperson problem, that the edge weights are non-negative. And the goal is to find a tour, a cycle of least weight. And here we consider a cycle to be a permutation of the vertices. Remember that every vertex must be visited precisely once, and at the end the tour must return to the starting vertex. And now what is the metric traveling salesperson problem? And for the metric version of the traveling salesperson problem, we add two more constraints. Not only do the edge weights need to be non-negative integers, but they must also satisfy the symmetric and the triangle condition of a metric. Right, so metric, maybe you have learned either in mathematics or right, in discrete math. I suppose you all have taken discrete math. This was one of the requirements of this lecture. In discrete math, you may or may not have learned what is a metric. A metric is a mapping from pairs of objects to real numbers, which satisfy the three conditions. First, the metric is always non-negative. So that's why we here consider only natural numbers rather than integers. Secondly, the metric must be symmetric. So the distance between two vertices between A and C must be the same as the metric distance between C and A. And the third is the triangle inequality. Right, so there's a question, are there non-metric traveling salesperson problems? Yes, exactly, that's the thing. Originally, I mean, the definition of traveling salesperson problem does not have such a requirement. So it may actually be, for some instances, for some inputs of graphs, it may be cheaper to take a detour from one vertex via one or several other vertices directly to the target vertex. And I agree that this is kind of strange or unrealistic and maybe rarely occurs in applications. Although when we, at the end of this chapter, when we talk about inapproximability, then we will exactly prove that a traveling salesperson problem without the metric hypothesis, the traveling salesperson problem for arbitrary edge weights cannot be approximated at all. So that means two things. Yes, indeed. Supposing that the distances between the points and between the vertices satisfy symmetry and triangle inequality, that the distances are a metric, that's a very reasonable hypothesis. But it also means that this hypothesis must be made, must be spelled out explicitly, not implicitly. And that's exactly what we do here in this slide. We suppose that the edge weights form a metric, they satisfy these additional conditions. Thank you for this question. I hope this clarifies things. If not, please then do go interrupt or ask again? Okay, right. So in this slide, we're going to consider traveling salesperson problem with this additional hypothesis. And we're going to devise and analyze an algorithm, which is called Christofides algorithm, for this restriction of the problem. And we're going to prove that this algorithm achieves an approximation ratio of 2, which, as you remember, is kind of similar, well, very vaguely similar to the ski rental problem, which also achieves our online algorithm. The break-even algorithm would achieve a competitive ratio of 2, right? In comparison there to the optimal offline algorithm, here in comparison to the optimal tour. So let's first look at the at the algorithm. The algorithm, the Christofides algorithm, was presented in 1976, and it's an approximation algorithm. It doesn't solve the traveling salesperson problem exactly. It doesn't give necessarily the optimal, the shortest tour, but it is guaranteed to give a tour which is at most effective 2 longer than the optimal tour. And this is going to be subtle and interesting in the analysis. And when we're going to analyze the algorithm, we need to somehow argue about the cost of the tour constructed by the algorithm and compare it to the cost of an optimal tour without knowing the optimal tour. But then again, if you remember, that's also true for how we compared, for instance, how we proved K competitiveness of the online last recently used algorithm. Then we also had to compare the cost, the number of page faults incurred by LRU in comparison to the cost incurred by an optimal offline algorithm without knowing what is the cost of the optimal offline algorithm. Anyway, so we're going to analyze Christofides algorithm, and this is a polynomial time algorithm. That's the benefit, right? We don't know whether the traveling salesperson problem can be solved exactly in polynomial time. Most people believe that it cannot unless P is equal to NP, but we can, at least in this setting, we can approximate it in polynomial time. So here's the algorithm, and the algorithm is, well, on this very abstract level, the algorithm is very simple. It consists of 2 steps. First, compute a minimum spanning tree. We already know how to compute a minimum spanning tree, right? Kruskals algorithm or Prim's algorithm. And this can be done in polynomial time. Actually, this can be done in, what did we see? Running time m log n or something, right? So very, very efficiently. Now take this minimum spanning tree and traverse the minimum spanning tree in depth first pre-order. Okay, that's a reference to your background on graph theory, graph algorithms, traversal, graph traversals from discrete math. If you don't recall, then for your convenience, I'm going to repeat that or illustrate that with an example. So here's the example. Okay, so let's suppose these are the points, and just for simplicity, they are located here on a grid, but we refer here to not necessarily grid distances between these points, but rather the algorithm can choose edges on the diagonal of the grid, just distances between vertices, and there's a total number of 8 vertices in this example. So remember, our first phase of Christofides algorithm is to compute a minimum spanning tree. So here's a minimum spanning tree. Okay. And now let's look at the root of this minimum spanning tree, let's say A, and traverse this minimum spanning tree. What did we say? Depth first, pre-order. What does it mean, depth first? You know, depth first algorithm, right? That's one way of recursively traversing a graph or a tree. And in pre-order. Pre-order means when a vertex has two successors, two children, then first visit the current vertex and then visit the children. So that's opposed to left root right traversal, which visits the left child first recursively, then the root, and then the right child. Here we first visit the root and then the two children. So this is our traversal of the minimum spanning tree in pre-order. So what does that mean? Start with vertex A. That's a root. So the root is visited first. That's pre-order. Then visit its left child and then visit its right child. Its left child here is B. And that's a recursive call. So not just the child, but visit the entire left subtree, visit the entire subtree located at B. So that the next step is going to visit the vertex B. Now this is recursive, so what will happen next? Pre-order means visit the root itself first, B, we've just said that, and then recursively visit the left subtree and then the right subtree. Left subtree is just a node C, right subtree is just a node H, so that this recursive traversal gives rise to the following order for visiting the vertices. First A, then B, which is so A is the root, which is visited first, pre-order, then left subtree B, in recursively left subtree C, then right subtree H, and then continue the recursion with the right subtree of A, which is the subtree located at D. So visit D first, then visit the only subtree of D, which is the one located at root E. Then visit Then visit the left subtree of E, then visit the right subtree of E, which is G, and finally return to A. Does that make sense? So this is a pre-order traversal of the minimum spanning tree T. Okay, and indeed you see that this is a tour, right? Every vertex is visited precisely once, and in the end we return to A. And we can do that for every minimum spanning tree, traverse that in pre-order to arrive at a tour. That's the algorithm, that's all, very simple. And we may give that to you as a programming assignment, which is going to be easy because you already have the minimum spanning tree part. Now the interesting and difficult part is the analysis of this algorithm. So let's do that. Let's compare that to an optimal tour. And in this example, for here, this lecture, we suppose the example gives the optimal tour. Let's say for some reason we know that this here is the optimal tour. Okay, this. Ah, yes, so when asked whether the choice of the root is arbitrary, that's a very good question, thank you. And the answer is yes, it is arbitrary. So if we have a minimum spanning tree, that's a minimum spanning tree with respect to any root. So we can pick any vertex and use that as root as starting point for the pre-order. Thank you, good point. Okay, so this is our optimal traversal, our hypothetical one. And what we want to prove is, no, this is our optimal to the right. And this is a traversal produced by the pre-order traversal of the minimum spanning tree. So A, B, C, H, D, E, F, G, H, and back. And this, let's say, is the optimal one. How can we compare the length of the two? We will denote by capital C the length, the total length, the cost of the tour provided by Christofides algorithm, and we denote by C prime the length of an optimal tour. And to prove that Christofides algorithm, that the tour provided by this algorithm has total length at most twice the length of an optimal tour, this is where we exploit the triangle inequality. The hypothesis is that we're talking about a metric traveling salesperson problem. Okay, so to this end, let F denote the sequence of edges pursued in order of the minimum spanning tree, right? That's what second phase of Christofides algorithm. And C denotes the cost of the tour. No, C denotes the tour thus obtained. That is, capital C is the sequence of vertices, permutation, starting with the first and ending with the same vertex. And C prime denotes an optimal tour. In general, there could be several optimal tours that all have the same cost. If there's some degenerate edge weights, then there could be several optimal tours, and it suffices for our analysis to consider just one of them. And we abbreviate, if we have a sequence of edges, the total length of the sequence is just the sum of the weights of the individual edges. That is convenient notation. Where we now prove the following three inequalities, they together then yield the claimed approximation ratio. So the first inequality says that the total length, the sum of the weights of the edges in the minimum spanning tree, is at most or is not larger than the length of the edges in the optimal tour. Okay, let me say that again. So T here denotes a minimum spanning tree, and there's no order of the edges in this minimum spanning tree. It's just a subset of edges. But recall our notation or abbreviation, simply add all the weights of all the edges. That's L of T. And on the right-hand side, there's the length, that's the cost of an optimal tour, which we don't know, but which we know exists, and which is our reference against which we need to compare. Okay, and the claim is that the total cost of the edges in a minimum spanning tree is at most the total cost of the edges in a tour. Why is that? Well, because the optimal tour is almost a spanning tree, right? So the optimal tour is spanning, right? It's a tour which visits every vertex at most once. It's not a tree. Why is it not a tree? Well, because it's a cycle, right? So if we remove any edge from the optimal cycle, then the result will be a spanning tree. Does that make sense? It will visit every vertex. That's a precise definition of being a spanning tree. So that means by removing any edge from an optimal tour, we arrive at a spanning tree. And a minimum spanning tree, T is a minimum spanning tree. Minimum spanning tree is by its very definition the cost of a cheapest of a least spanning tree, therefore it cannot be larger than the cost of C prime. Does that make sense? So that's all proof of the first inequality. Now for the second inequality, we observe that every edge that is contained in the minimum spanning tree occurs precisely twice in our tour, in the tour as traversed in order. So that gives rise to the second, which is actually an equality. The total cost of our tour, the sequence of edges pursued by the in-order traversal, not the sequence of edges that are actually output, but during the in-order traversal. Let's recall the in-order traversal in this example. So the in-order traversal says first visit A, then visit B, then visit C, then visit H, and then jump directly to D. Now we cannot directly jump to D, right? So that means in the in-order traversal after visiting H, we kind of return, we traverse this edge a second time. We've already traversed it the first time when we came from B to H, and now we retract basically on this edge. We also traverse this edge a second time backwards, and then we get to D. Then we get to E, then we get to F. From F we get to G, but we cannot jump from F to G, so we need to traverse these two edges. So this edge is traversed the second time in the opposite direction. And finally, from G we return to A, but we cannot jump from G to A, so again we traverse this same edge again in the reverse direction. We traverse this edge again in the reverse direction. We traverse this edge again in the reverse direction, so that actually the in-order traversal visits every edge precisely twice, whereas it outputs every edge only the first time it is visited. Therefore, the total cost of the traversal is exactly twice the cost that is actually output by the algorithm, by the Christofides algorithm. And the third inequality says that the cost of output S by Christofides algorithm is at most the cost of this in-order traversal, so that we will prove that next week. Time is up, but let me just conclude by showing that altogether these three inequalities give rise to the claimed estimate, namely the cost of the tour output by Christofides algorithm is less or equal the cost of F by inequality 3. This is twice the cost of T by inequality number 2. And this in turn is at most twice the cost of the optimal tour by inequality number 1, so that the cost of the tour output by Christofides is at most twice the cost of the optimal but unknown tour. Okay, so that's all for today. Next week, Tuesday, we're going to reconsider again. I'm going to explain Christofides algorithm again, and then we proceed to approximation algorithm for the knapsack problem. Thanks everyone, thanks for your attention, and have a great rest of the week. Bye.